Everybody, this is Larry. This is day 31 of the December Leetcode Daily Challenge, last day of the year. Hope everyone had a good. I hope everyone had as good a year as you can have given the circumstances, and hope everyone stay healthy and take care of yourself and all that stuff. And happy New Year if I don't see you before then. I know that this is not a regular intro, but it is the last day of the year. Hope you've been keeping up the streak. But yeah, while you do that, hit the like button, hit the subscribe button, join me on Discord, ask me questions. I usually solve these live, though for this one, I've seen it a couple of times. So I think I have a good idea of how to go, but I usually go over my thought process and not just, the solution, because then it's just someone reading you the solution. So feel free to fast forward or whatever you need to do. I'm not going to take offended. But yeah, for today's problem, we have a classic problem of sorts called largest rectangle in a histogram. I know enough about this problem, but I don't memorize solutions. So we'll see where that goes, where that takes us. So okay, let's make sure that I get through this real quick. Given n of these represent, find the area of the largest rectangle in the histogram. Okay. So so area under a histogram, and basically, well, what I'm going to say is that there's some if you're looking for keywords, you're gonna look for monostack, monotonic stack, something like that. But what I hate about monotonic stack or monostack when people use those words in general is that they describe a property of what is an emergent property, right? And what I mean by that is that it is a property that comes up by using a stack because you're using an invariant in some way, and because of that, it is more important to discover the invariant and that you need to use stack rather than it's not like some crazy new data structure and just like practicing these problems is not going to help. Because not help enough, because the critical skill of solving these type of problems is trying to find the invariant as you go on. And hope that makes sense. And for this problem, the invariant is trying to figure out, okay, given a current, we're going to do some kind of, wouldn't say is a sweep line per se, but you're going from left to right or right to left. It doesn't matter because it's symmetric. The problem I would ask is, okay, given this new strip, this height, what is the biggest area that I can find, right? And how can we do it effectively or efficiently? And well. And yeah, and the answer is, just try to figure out, and yeah, and the answer to that is just trying to go, you could kind of find this, I'm trying to describe this, and maybe I just need to pull off a Microsoft Paint, and let me do that, hang on. I am recording this live, so apologies for that, but let me pull my drawing stuff. Okay, so basically the idea is that without taking necessary advantage of ongoing things, let's say we have some histogram thing. They're all the same width. I'm just not drawing it that way, right? And then the idea is, okay. Oh, well, one more thing that I would say is that looking at this problem again, then they don't give you the constraint. I'm going to assume that the constraint is that n is big enough that, is linear time. Because if it's not linear time, then, not linear time, but at least faster than n squared. Because n squared is the naive way of doing it. And if you're doing it n squared, you're going to get the right answer. But it's going to be too... I assume that it is too slow, otherwise it's not interesting, and it's two for loops. Anyone can do it for the most part, right? Anyway, so that being said, well, then then we're just for each skyscape, and this is our sweep, so we can ignore the right side of it for now. Is that let's say we're looking at this rectangle, right? Well, the question is, well, we know the height of this, but and then the question becomes, okay, we want to check this. We also want to check. Oops, let me use another color. We also want to check, given this height, the longest that can go to the left. So then, you have something like this. You also want to check this, this area. You want to check this area. You want to check this area, right? So of course, if you do this, naively, you are still going to get n squared, which is what we're trying to avoid. Then the question is, okay, can we construct this in a way such that, well, you try to find the invariant of, okay, we only need to check two things, right? One is that, construct it backwards, is that we can check only this thing, right? Well, actually, you don't even have to check. Man, I have the invariant, but I'm explaining this very poorly, and I'm apologizing. But okay. So now we know that if we add, okay, yeah, I think the way that I want to do it is, okay, now that we added this, and it is strictly higher than the last one, then I think we're okay, because now we want to figure out, in a way, if you look at this last rectangle, you can imagine that this goes on infinity, going the other way. I might have to edit this down a little bit, right? And then now the question is, how far does it extend infinity, right? Well, we'll worry about that later when we add another thing. And then now the question is, okay, so then we have this other thing that we slide to the right. Sorry, I know how to solve this, but I'm trying to think out the best way to explain it, and that's some of the struggle, and I apologize for that. But then now let's say you added this orange thing, right? Well, now you know that trying to mix colors. That's what I'm so. Well, you know that here it's no longer true, so this is the end of that length. So yeah, so we have to do some maths on that, because then now we can check whether this is the longest, the biggest area, right? Otherwise, for this element, well, and we also do the same for here, right? Because this is no longer going to be part of the, because this, because of this space here, this area also has to be removed. This is also removed, and so forth, right? All the way up to here. And now we can combine this current check with, okay, this is actually coincidence that they're the same height, so this is a little bit of a bad example. But then now we can check this area here, right? Because now we know that, we know that, this thing extends all the way to the right, at least up to this point. And also in this case, as we're going from right to left, looking back in history, here, well, we know what the width this is, right? So then we're able to calculate the area and whether, now we know how far it extends before it hits the empty space. So then now we're able to, figure it out. We're able to figure out the area and whether this is the biggest area. And it's not, we don't even look at just this area. We actually look at this entire area, because now we know that this is the extent of which is what it extends to, right? And then as we go through the right, we also do the same thing with respect to here. And what I mean by that is that now, oops, wrong thing. Now we also do the same thing with this rectangle, because we now know that with these corners, this only extends this way. Well, technically, we would go to here, but to calculate the area that way. Okay, so that's basically all the foundations for this problem. I honestly also don't think I explained this really clearly, but basically now we have two cases of, okay, now that we're inserting a thing, we're trying to clear things to the left, and in an ongoing kind of way, like it's almost kind of like similar to sliding windows but backwards with a stack, where with sliding windows you can imagine sliding windows as a queue. Here it's a stack where you're going backwards of, okay, now I have this new constraint. The invariant is that you clear the things from the back because they no longer be true, right? Because looking at this map again, we know that with this height, it has reached the end of the road, right? Because it does not have, it cannot go to the right, and we know that it cannot go to the left at this height, because otherwise, we would have done it previously. So yeah, and in here on the left, and then in a way that is recursive, that's the way I would think about it. This is also probably why I don't record these things at the end of a 5-hour stream, because I think I'm a little bit tired and the explanation suffers a little bit for it. But hope that makes sense as we get to code. So now we're going to start with a stack. And I think for me, the way that I like to do these is I start by, like an edge case, right? Because if you have to do an edge case about the left edge and the right edge, the way that I want to just fix the edge case while thinking about it is just adding zeros at both sides. Because once we add a 0 on both sides, then that means that you just have a height 0, and then everything clears from the end. Okay, now let's say n is equal to this new height, and then now for index height in enumerate heights. Oops. Okay, now we build this structure one by one, and hopefully this part is a little bit better with respect to visualization, which is why maybe I don't do the visualization that much. But okay, so then we try to do a precondition of, okay, if the stack is greater than 0, then what happens, right? Well, if and the thing to notice is that, as we were talking about in the graph or in the picture, if this current height is smaller than the previous height, then we have to process it, because of the previous height will not be good enough, right? Because the previous height now its journey ends here, because at the previous height it's going to be capped by the current height. So let's kind of do that. So the top of the stack, let's store it in the first element. It doesn't. Oh, I guess this is also where I can use walrus operator, right? Maybe. Actually, I don't know if this has the new walrus operator language. I'll test that later. But yeah, while this is the case, what do we do? Well, we want to process it, because we now know that for that column, it no longer extends to the right. So then now we take the previous index, which is so this previous index, if you look at and I hope that you draw this with my explanation, the previous index is the index that begins, like, it's essentially the width of that the column, and previous index will allow you to calculate that, because each column is of height 1 kind of, right? So then previous index, previous height is equal to the top of the stack. And then now, oh yeah, let's keep track of the biggest area. So let's start it by 0. I just call it best because I'm naming things so hard, so I just always call everything best. So the best is equal to just the max of best, or the difference in the indexes. I may be off by 1 here, but I have to double check that. And yeah, so the area is just width times height, so it's this times the previous height, right? And then that's pretty much it for this part. You pop it to get rid of it, except for now. One more thing to notice is that one more thing to notice is that now, if you go back to the visualization that we had, the index to the left now, let me pull it up real quick. This is a little bit of a mess, but yeah, let's say we look at this orange blob, right? Now, you could think of us as chopping off. We chop off this. Whoops. We chop this off. We chop this off. This was already chopped off, to be honest. So this was already no longer here. But what happens is that now we want to extend our current thing all the way to here, right? So then now we have to kind of move our current index to the previous index as a result, because now we know that that's how far our current height extends. Hey everybody, so at this point I edit this later because I made a mistake, and basically my picture was blocking the entire code view. So what you see next is just going to be, I'm going to keep the talking head, but it's going to be me statically looking at the code. So you can follow through the code, even though I already typed it and finished it. You can follow through the code as I'm doing it live. My apologies. Happy New Year, and yeah. So okay. So then now, now we want to do something like set index is equal to previous index, except for that, because you want to keep on getting to the last index, but so we should probably redeclare it here, just to the none. If this gets activated, this gets set. So if previous index is not none, right? And then at the very end, we have to push back the stack, which includes the current height and then the previous index, or the current index, which may be the previous index. And then at the very end, we can just return best, and that's pretty much it, I want to say. Let me run the code real quick. 25 is not right. So maybe I do have an off by 1 somewhere, or just really bad code. And what I do with these, when I do run into a bug, is try to figure out, if I had some invariance that I thought it's true, it's not true for some reason. And that's a little bit unfortunate after all that spiel. Do I have another test case? No? Okay. So here I want to start by just like having a small obvious case, and maybe some bigger ones just to kind of see. So it may be that I just have some like weird edge case, even though I thought I didn't for some reason, but why is this? Dun dun dun. So 2 elements is always just really wrong. do something funky. I don't even use it. And so one element, we always push this anyway. Let's look at the stack. Let's look at the stack as we go through it then. Stack is 0, 0. You have 2 at the index 1. That's good. Let's look at the more obvious ones first. 0, 0. What? Did I put in the wrong order? Oh yeah, okay. That's just me being silly then. I put the previous index first. Maybe because I was talking about it. Oh, okay. Whew, hopefully that's it. So there are like silly mistakes like that, and it happens. Is that good? Okay, so this looks much better. Oh, okay. So, you know, like I said, even I make mistakes a lot apparently. Yeah, and then for now I'm gonna just try some big random number, and then after that gonna submit it as a result. Okay, looks good. Let's give it a submit. Whew, okay. Yeah. So I think for this problem, I know that my explanation was probably not the best because it's not prepared. I don't know the problems ahead of time. So there are definitely probably better explanation videos out there. If you want to know the intuition for, or like if you want a detailed explanation of this problem. But what I can do is kind of go over the invariants that make this possible and kind of the keynote to translating what's going on and what's in this problem in terms of implementation. And the key thing to note for this problem is just that you know, just trying to find an invariant, right? Which is that you know, the stack. I know that, like I said, it's monotonically increasing, but if you look at this problem, the way that I write it, that actually, you know, we don't actually assume that, or we don't need to assume it. It just is an emergent property of how we design the invariant. And for this problem, the numbers do get smaller as you go from right to left on the stack, because if you think about our visualization again, we're trying to look at each column and see how far it extends to the right and to the left. And to the left, if you have like almost a contradiction where you have a smaller later number, well, that smaller number, or like that number is already, like the journey has already ended for the taller building, because that taller building can no longer extend to the right. So in that sense, that's why you keep on popping it until, you know, the building is smaller, and then at the very end we do this calculation because, well, this previous index is, if you want to look at it as a breakdown, the previous index is actually, you know, the thing that's on the stack. It allows you to look at, for this height, how far it extends to the left it is, right? And there's some magic that's hidden here a little bit, is that the current index will tell you, well, this is where it ends on the right. So, which is now, and the current index, right? So basically it becomes a sort of, if you look at it in a sliding window kind of way, this is just, you know, the right pointer and then the left pointer, and this is how this width comes about. And then, of course, as a result, going to the left, going to the future for this current height, you know that you're able to go to the previous index as far as you can go, because if you go further than that, well, the height is smaller than you, or your height, so you cannot go further than that in the current height. And that's the way that I would think about this invariant. This is a kind of a long video, but for something that's like this. But yeah, so what is the complexity of this? So I'm explaining it in a very naive way, well, which is that, okay, you have one for loop and you have a while loop, so obviously it's going to be O of n squared. And in terms of space, you have a stack, so it's going to be O of n space. So obviously it's going to be n squared time and O of n space, right? Well, it turns out that, of course, if you look at it that way, it's going to be O of n squared. But there are other ways to analyze the time complexity, and for this problem, as I alluded to earlier in the video, so which is that for each item in height, we are going to only push it to the stack once, because there's only one push for each number in the height, and we're only going to pop it off the stack once, right? So in that case, in that sense, each item will only be popped or pushed a constant amount of time, and so and these operations only happen when an element gets popped, right? So in that sense, even though in one loop we may pop multiple items, each item individually will only be pushed or popped once, which means that and there are n elements, so that means that in total there'll be O of n time. I think that's all I have for this problem. Let me know what you think. I know that the beginning, especially the graphic, is probably a little bit poor, but that's okay. We're all learning here. I'm learning how to explain this problem a little better, hopefully for next time. But yeah, let me know what you think. Hit the like button, hit the subscribe button, join me on Discord. This is the end of the year, so I am gonna end this segment with just just my thanks in general. Thanks if you watched this far. Well, thanks for watching. Thanks for the support. And thanks for just this has been a tough year, obviously. But making best of it, and if you're improving your skills in a safe way, there's no better thing. I do hope everyone stay safe, stay healthy. Take care of yourself, both physically and mentally. And if you're fortunate enough that you feel like you're taken care of, either by yourself or by others, then pass that along. Take care of other people in your life, and maybe even not necessarily in your life. Do good, do well. I hope you had a great year, especially given the circumstances. But I hope you have a great next year. Happy New Year, and I will see y'all, next year. Bye-bye.